thank you very much for the invitation to be here. So today's talk is about the following basic question in automorphic forms, which is probably nonetheless, in the generality that I'm about to state it, way too difficult to be tractable. But the question is, so given a reductive group G and a finite dimensional complex representation of its L group, so I'll call that R. So it goes from LG to some GLV. How many automorphic representations of bounded analytic conductor are there? How many This is just a vague statement, so I definitely want some other adjectives here. So let's say irreducible. So the talk will be about a special case of this. So this is just kind of a vague statement for starters. Conductor. So this is analytic conductor with respect to R. So analytic conductor less than X. Are there? Okay, so I think of course, so this representation of the L group is going to, by the Langland's functoriality philosophy, that should give us an embedding of the automorphic representations on G into those of GLN for whatever dimension this is. So the subject of today's talk is going to be a very special case of this. So it's just going to be the case that G equals T as a torus over a number field. OK, so before I go further, the talk also comes with an acknowledgement section. So the work I'm going to talk about today grew out of some early conversations with Hunter Brooks. And Will Sawin. And so, yeah, some of the ideas came from them. OK, so the set I'm going to be interested in is the set of continuous unitary characters of T of the F adels mod the F points of T. So I'll give this set a name. It's the set I'm going to try to count. So I'll call it A of T for automorphic characters of T. And so what I'm also going to do is I'm going to pick new, a Haar measure on A of T. OK, so I'm going to kind of start out by just pinning down exactly what this notion of analytic conductor is in this context of the torus. So I better start by saying what, writing down the representation of the L group. So let me say what the L group is. So T hat, this is going to be the complex dual torus of T. So this is the co-character lattice into C cross. It's a number of copies of C cross to the dimension of T. So it's complex. So let's say L over F is a Galois extension of number fields splitting my torus T. And then I'm going to let G be that Galois group. And so G has an action on the complex dual torus because it acts here. And then we're going to have the L group. LT is just going to be T hat semi-direct this action of G. And so what I'm going to do is I'm going to pick now a representation R from LT to GL MC. So this is a complex algebraic group, and so is this. So I also want to demand that this representation R be algebraic. Okay, so given those things, I want to talk for the next few minutes about what, just how to define the analytic conductor for a character, an automorphic character in A of T. Okay, so this section here is called analytic conductor. So the analytic conductor is an everywhere local invariant of elements of A of T. So if I take chi, an automorphic character, and I can decompose chi over places, chi v, then I'm going to write the analytic conductor with respect to some representation of the L group R. So this will be, in terms of a product, also over places, of some local analytic conductors, which I'll abuse notation and use the same CR of maybe chi v to denote the local analytic conductors. OK, so I'm going to tell you what. So these are one for all but finitely many places. And I'm going to tell you what each of these local analytic conductors are. OK, so now for the next few minutes until further notice, L over F is going to be an extension of local fields, where L is the splitting field locally for the torus. OK, so I'm going to need the group. So it's the elements of the absolute Galois group which act by an integer power of Frobenius on the maximal unramified extension of F. So I also need the relative. OK, yeah, in the p-adic context. So I won't say what it is in the Archimedean context, but everything else will hold for Archimedean also. So here's the relative Weyl group W L over F. So this is just WF mod commutators from WL. And this has a WL abelianization as a subgroup. So a nice way to think about this relative Weyl group is as a group extension. So W L over F is an extension of just the Galois group of L over F by L cross, where this is the Artin map. And so I'm going to give this projection map a name. It's called sigma. OK, so then the theorem, so a theorem due to Langlands. So this is just the local Langlands correspondence for tori. So I'm going to define these by going through this local Langlands correspondence for tori and pulling the conductors from the Galois side. So this just says that So TF, this here means Pontryagin dual. So this is isomorphic to this group cohomology group, so W L over F T hat. OK, so if I take a chi, which is a character living here, and let's say it corresponds to rho living here, then if I take rho cross chi, this is now, so this is just a cocycle, but if I take rho cross chi, this is going to give me now a Langlands parameter. So this actually goes into LT, so that gives you the Langlands parameter. OK, but I said I wanted a complex Galois representation so that I could pull the conductor from that complex Galois representation. So now if I take R composed with this Langlands parameter, this is going to give me a legitimate Galois representation. So this goes now to GLMC. OK. I don't know, maybe I'll write over here now. OK, so then the definition of what the local analytic conductor, CR of a chi, so this is going to be, OK, the conductor of the corresponding R composed with the Langlands parameter. So, where, OK, what does this C mean? So where C of a representation V is the Artin conductor, if we're in the non-Archimedean setting. So if F non-Archimedean and it's the analytic conductor, if we're in the Archimedean setting. So maybe let's see. Any questions up to this point? OK, so I think that's all I'll say about the conductor. Let me just check my notes to make sure I didn't forget to say. OK, great. Yeah, in terms of the gamma factors. Exactly. So if I take, let's suppose L over, let's suppose L over F is like R over R. So let's say my torus is split over R. Then if I go WR over R, let's say I actually write, so I go WR to WR over R to T hat semi-direct 1 because I'm in the split case. So this is just locally, this is the L group if I'm in the local setting now. And now let's say if I call this this map phi, then the possible phi are parameterized in the following way. So so maybe I should say WR. So this looks like C cross disjoint union with another copy of C cross, and I'll distinguish it by this some element J, and this satisfies the following rules. So that's just a concrete description for what this Weyl group is in the Archimedean setting. So then these are parameterized by phi of z is like z absolute value to the W1 z absolute value to the W n. And then phi of j is -1 to the, let's say, epsilon 1 up to -1 to the epsilon n So here, the wi are imaginary numbers, and the epsilon I are in 0, 1. So that's like the sign. OK, and then I have to tell you, so I need to bring in my representation R. So so I only care about R restricted to the connected component of the identity. And so let's say R of z1 up to zn. So let's say this looks like a product of zi's to some exponents. So this is like I equals 1 to n. N is the dimension of the torus. And here these mij's are actually integers because of my algebraic assumption on the representation of the L group. So then the L factor at infinity associated to this phi and associated to this representation of the L group. So I can write this down explicitly in terms of gamma functions. So this is a product j equals 1 to the dimension of the representation of gamma r of s plus. So this is the standard dot product. Here I've got m j w, where w is the vector of w's over 2 plus. So there's a number here which is 0 or 1. So it's mj dot with epsilon mod 2. So this is the local L factor infinity, and then finally the conductor chi. If phi corresponds to chi under this Langland's theorem, then this is the product j equals 1 to the dimension of r of so it's the absolute value of this stuff on the inside. So absolutely plus, and then let's say 3. So you could see some data depending on both the representation of the L group and the Langland's parameter. So in general, if I have a torus over R, it's a product of copies of the circle or C cross or R cross. And so this is like the R cross case, but you can imagine there would be 2 more cases to work out that you could do by hand. So that's what at infinity it looks like. OK. All right. Let me. OK, so I want to. That's all I'll say about the analytic conductor. So I have to state a couple more things, and then I'll state the theorem. So here's a couple of definitions that I have to use to state the theorem. OK, so if I take my representation of the L group and I restrict it to t hat, because of the algebraic assumption, this breaks up into a direct sum of one-dimensional eigenspaces. So they're indexed by characters of t hat, which is the same thing as co-characters of t. And there might be several one-dimensional spaces with the same character here, but they're all one-dimensional and acting through this character. So maybe I'll, OK, so you have some decomposition like this. And then I'm going to say I'm going to let, I'll let curly braces mu I equals 1 to dimension of R. See, this is going to be the multiset of co-weights. Co-weight. So it's just the set of characters that are actually appearing in this decomposition with their multiplicities. OK, so S now, and this is going to come up through a lot through the rest of the talk, S is going to always denote a subset of co-weights. And then I'm going to let D of S. So this is going to be a complex diagonalizable group. So it's the intersection of the kernels of the mu i's sitting inside. So it's inside T hat. And I'm intersecting over all the mu I which are in S complement. So this is the complement of S inside the set of co-weights. OK, and then I take the intersection of these kernels, and that gives me some diagonalizable group, subgroup of T hat. So what this looks like is just the number of products of copies of C cross and some roots of unity. OK, so it doesn't have to be connected, but each connected component looks like some products of C cross. OK, so now there's an important assumption. So we're going to suppose R restricted to T hat is faithful. So in particular, faithful implies that D of the empty set is just the trivial subgroup of T hat. So maybe because this thing is in the way, I'll not write on this board, but leave that up there. So I think this will go up here. All right, so just assuming faithful now, I'm going to define this important number, which we'll call A. It's a rational number. It's a positive rational number. So it's just equal to the max of the following finite set. So it's the max over the dimension of D of S plus 1 over the cardinality of S. And I'm going to run through all of the S such that D of S is not the trivial group. So in particular, because I assume faithful, this makes sense because the empty set is not allowed. OK? So here's the theorem. So I'll suppose R restricted to T hat is faithful. So then there exists a polynomial, a non-zero polynomial, so P is going to depend on the Haar measure nu I picked, and it's also going to depend on R and T, and a positive number delta, so that the Haar measure of the set of automorphic characters with analytic conductor less than or equal to some big number x is equal to x to the a power p of log x plus an error term of x to the a minus delta, where here again the constants depend on everything inside except x. So it depends on nu, t, r, the number field f. I guess this depends on f also.
What is A?
A is this number.
So
A doesn't have to be an integer?
A does not have to be an integer. And if R restricted to T hat is not faithful, so then the left-hand side is equal to infinity for some finite x. Yeah. So some.
Completely irreducible.
Yeah. So some subfamily that's a functorial subfamily of the.
Most of these are coming just from the dual of the torus, right? I mean, there's a this log x seems to indicate a hyperbolus.
So I don't think the log x just comes from hyperbola. So I'll give a few examples.
But are most of these guys, I mean, if I had finite Galois representations, which were,
So if I like.
we're taking representations of GL, which was the absolute, which was the Langlands dual with the Galois group in it.
Yeah.
Not just
Yep.
characters.
Yep.
Suppose, I guess this boils down to whether you're faithful or not.
So the Archimedean.
T is trivial, or T is one-dimensional torus. What are we talking about?
Well, if t is trivial, there's nothing to count.
Why aren't you counting then? I don't know, T trivial is not accurate.
Yeah. But I see.
They must be occurring. Can you give us another description of what you're counting?
So I don't know. I mean, it's characters of.
One over another.
Yeah. So that's a great. So that here, example one.
Character,
Yeah. So example one. So the simplest possible example is, so I'll let t be just gm. So the same thing as gl1. Yeah, sure. And so in this case, the t hat is just c cross. And so I'll pick R to be the identity map from C cross to C cross. It's a one-dimensional representation. It's faithful. So what this is counting is the set of Hecke characters, primitive Hecke characters. I wrote the word Hecke here. So this is the standard analytic conductor in the standard sense. And so then this Haar measure is just going to be, okay, so there'll be some, yeah, it's the same thing. Yeah, Hecke-Grossen characters, yeah. And so there'll be some like, yeah. So there'll be some parts which are like absolute value to the IT, and on T I put Lebesgue measure, and then all the discrete part I put counting measure on the discrete part. So by uniqueness of Haar measure, that's. Yeah. Yeah. So A is 2. So can work out in terms of these groups D of S, etc. So what? Okay, the S's, there's only 2 subsets S, the empty set, and so I'll write by Z is the identity map. So here D of empty set is just 1, and D of the whole thing is C cross. This set is disallowed by this condition. So there's only one set in this max, and the answer is 2. So this implies A is equal to 2, which is what we expect. We expect this to be some constant times x to the square. So this is something that sort of, for example, if we take Q, this is just primitive Dirichlet characters along with the character n to the IT. And we know from classical considerations that's the right order of magnitude. So maybe a less trivial example. Here's example 2.
What is P in example 1?
P. Oh yeah, P is a polynomial.
What is it?
So well, there's going to be a second theorem in the talk where I can tell you what the degree of the polynomial is. I can't give you any sort of coherent expression for what the coefficients are, but I can tell you what the degree of the polynomial is.
And in example 1, what is
The degree is, it's a constant. Its degree is 0. Yeah. So example 2 is, I'm going to take the restriction of scalars L over F of GM. So this, the automorphic characters of this would be Hecke grossing characters of L viewed as automorphic forms defined over F. But I'm not going to count this. I'm going to take a subtorus of this. So that's the torus of norm 1 elements. So there's a Galois action on this, and I'm going to take norm 1 elements. So this is the norm 1 subtorus. So maybe if I write the degree of L over F, if I say that's n, the dimension of T is n minus 1 now. OK, so if I want to feed this into this machinery, at least to figure out what the power of x is, I should write down what the dual torus is. Eraser, here we go. OK, so in this case, T hat, I can consider it to be the following concrete thing. It's n tuples in C cross to the n. So this is the dual group of res L over F GM, but such that Z1, the product Z1 up to Zn is equal to 1. So G now, I never said we're back to the global case, obviously. So this is going to be the Galois group of L over F. And so this acts on T hat by permuting coordinates. So maybe I'll think of this as a subgroup of Sn, of the symmetric group on n letters. OK, so here's the L group. And I want to pick a representation. So here's one that seems very natural to me. So here's so R on Z1 up through Zn, semidirect 1. So I'm going to send this to the diagonal Z1 up to Zn. And then I'm going to take R of 1 semidirect G, where G is in the Galois group. So I won't write it in this bad way. I'll just write G in G here. This is equal to just the permutation matrix that G defines on these guys. So between those two, that's enough to determine this representation. OK, so what are the co-weights? The set of co-weights if I restrict to T hat. So they're just the set of, so I'll write Zi. These are projections onto coordinates. OK, so S, well, OK, so S is a subset of these. So kind of the crucial fact in this example is that the dimension of D of S is always equal to S, the cardinality of S minus 1. So I'll say S not empty. So OK, this is a subgroup of this n minus 1 dimensional complex torus, and it's this dimension. So this implies that A is equal to 1 in this case. And this will come up later, but it's important to note that this max here at the top of the board, this is attained for all the S, I guess all the S of size at least 2. So max attained for all.
Let's see, there's some finite dimensional, in this case, the kind of representation you're getting is not going to be a Arden type representation twisted by these Grossen characters, basically, and the Grossen characters are where all the many are coming from. Once you found the conductor. In other words, so what L function do you get out of this in this case? It's not a heck L.
No, I don't think it's a heck L function. I think, yeah.
It's probably an induction, I think, of a character, of a Hecke character from, is it induced from a monomial?
Well, they're not always going to be Hecke characters. I mean, here I don't have, but
They seem to be, I'm trying to understand
yeah,
the description of what you're counting.
yeah. So really, all the counting happens on the Galois side. So really,
In the end, you're just going to be looking at the dual torus. It's all going to be coming from a harmonic analysis of the torus, right? It's not going to come from the non-abelian part. Is that correct?
Well, it's going to break.
Yeah, you had a thing into GLR.
Yeah.
The R here is going to be what, n minus, depending on what the irreducible representation of this finite permutation matrix is.
Yeah. So,
I guess,
I mean,
are you constructing something like some finite Arden representation and then twisting them by Grossen characters?
no, I don't think so.
No?
No.
Give us a description of the family. That's
I think in general, writing down a torus and a faithful representation and saying what the image is quite difficult.
Gave us its Hecke characters.
Yeah.
In GL2, the simplest example.
Okay, sure. Yeah, that I can say something. So let's just take this example that I have on the board. And let's just take the case that T is one-dimensional non-split torus. So in that case, I'm going. It splits over Z mod 2, and I'm going to use Hilbert theorem 90. So in that case, there's an exact sequence like this, where here is forms on. So this is GL1 over the top field, and then the co-kernel here is exactly GL1 over the bottom field, where this map is a psi here, say, maps to psi of x over x Galois conjugate. And so the image of this inside this is exactly those Hecke characters, which are trivial on the adels of the lower field. And then once I'm in GL1 over a number field, then I can move to GL2 over this number field by base change, and it's exactly the subset of the image of the base change map, which are characters that come.
Base change of the first example, more or less. It's a
Yeah.
base change.
Yeah, but there's a condition now. Now the condition is that it's trivial on F, so that's what's cutting out this subfamily. Yeah. So I think there's kind of.
The deformation space, when you're making many of these, is somehow coming from a dual torus, from the torus. That's why you can count it. That's what I'm trying to point out. So
Okay.
Somehow you're twisting by characters or inducing. Sort of the beef in the family are just characters. So
Yeah. I'm certainly just counting.
one-dimensional characters.
Yeah.
I mean, there's an old theorem of Jordan. If you have a finite subgroup of GLNC, there are only finitely many finite subgroups of GLNC, except for abelian by finite, except for this kind of things by these abelian things. So I think that's somehow what's limiting. And the only way you can deform is by twisting by characters.
Okay.
Or things
Well,
like
I don't see how the twistings come up, but maybe you can explain more to me how. Yeah.
Anyway, this example has that because you're varying
Yeah.
somewhere else, and there they're just characters, and then you're doing base change. It's true you've got an extra condition.
Yeah. So, I mean, in general, you can make some family and that'll be cut out by some conditions.
Like one could ask what for the universal family.
Yeah.
How many automorphic forms are there on GL2 of conductor less than X, and we're trying to see
Yeah.
which ones you're counting.
Yeah. So, I think, in general, if you want to know what give some characterization of the image of this local Langlands correspondence. I'm going through the local Langlands correspondence to make sense of everything. And I think characterizing the image of that in general is pretty difficult, right? Or is it easy in the case of tori, or?
I don't even know that your examples that you have here, the L functions are known to be entire. That's what I was asking this question.
Ah.
In other words, you're counting.
Yeah. I don't know what the L function of one of these guys looks like, but I would have to think about it. Yeah. So. OK, so as I promised, I can say something about the degree here, but I have to make a few more definitions. So let me make those definitions. OK, so
See, I mean, the fact that it's x to a power a, and a is somehow a dimension of something means there's some deformation space that's responsible for this.
OK.
There's no doubt.
OK.
I mean, it might be a fraction, but it's still this. That seems to be indicate to me it's sort of one-dimensional deformation.
Mm-hmm. OK, so to kind of continue and try to give some of the definitions, which well, you're going to tell me what this degree is. So this is my global Galois group. So this acts on the set of co-weights. So of course it acts on co-characters, but it actually preserves the co-weights. So it acts also on these subsets S. Set of S such that S is inside the set of co-weights. So this action is going to preserve. Action preserves. So of course it preserves the cardinality of S, and it also preserves the dimension of this complex diagonalizable group D of S. So I can make the following set. I'll call it sigma. So it's the set of S, let's say non-empty, such that the S is attaining the max in the definition of A up there. Equals A. And so G is going to act on this set sigma. OK, but there's a second action, which is important to state the general theorem. So I'm going to let lambda. Lambda is going to be a non-negative integer, a positive integer. So this is going to be the LCM over all the S's of the cardinality of the component group of D of S. OK? So then Z mod lambda invertible. So this acts on pi 0 of D of S for any S. So just by, say, L in here and, say, Y in here, L acts on Y by raising to the Lth power. OK, and now to state the theorem in general, I want to take these two actions, one on component groups and on the sigma, and put them together. So I need to take my group G, and I need to enlarge it just a little bit. So I'm going to let L tilde be L adjoin the lambda roots of unity. And then G tilde is going to be Galois group of L tilde over F. So then I'm going to say sigma tilde is going to be it's going to be a fibered set. So it's the set of pairs S comma Y such that S is in the base. The base set is going to be the sigma, and then Y is the fiber. So in connected component. So G maps by restriction, G tilde maps by restriction to G cross, I'll just say G cross Z mod lambda cross. So let's say that if I have a G here, I'm going to write it as G bar G star. So that's this map. And then, so then this is going to act on sigma tilde by G bar G star acts on a pair S Y by G bar S G bar Y to the G star. OK, so I have to edit this set one more time. So I'm going to G sigma tilde, and I'll put a 0 here. This is just the whole set sigma tilde. Delete this subset, which is fixed under this G tilde action. So it's the set of pairs S comma 1, such that the dimension of d of S is equal to 0. OK, so this set here is preserved by the G tilde action, so I can throw out that orbit, and I'm left with this set. So I'll give a concrete example of this after I state the result on the degree of P. So maybe I'll erase this and leave the theorem up. Yeah.
Finite order here.
No.
You did say you were going to work all on the Galois set.
Yeah.
He's made this extension. This is what the Weyl group extends the L group to allow Hecker characters. That's one of the reasons he found, because he wanted to have Hecker characters not of type A naught.
Yeah.
Yeah, but how is he going to have
That's a Weyl group part. That's exactly the Weyl group part.
Yeah. OK, so the second theorem.
I mean, he wanted to be too close.
Is that the degree of P. So I'm going to take this fibered set, and I'm going to take the set of orbits by G tilde. I'm just going to ask for the cardinality, and then I'm going to take away 1. So that's the degree of P. So I think it's, let's come back to example 2. And let me just say what these sorts of objects mean for example 2, which we already talked about. So in this case, d of S is connected for every S. So this implies this number lambda is just equal to 1, and G is just equal to G tilde. And then I think I said on the blackboard, which is still up here, I have this formula for the dimension for every S. And it's actually going to attain the max for all S bigger than or equal to 2. So this implies that this set sigma is the same as sigma tilde, is the same as the set of subsets S of cardinality at least 1. So just every single set S is in this sigma. And then because I have lambda equal to 1, taking away this set to form sigma tilde 0 just deletes exactly all of the S's of size 1. So sigma 0 tilde set of S such that the cardinality is greater than or equal to 2. Which is a pretty big size for that set sigma tilde 0. So now I'm going to suppose that the global Galois group is the full symmetric group on n letters. And so this is going to imply that there exists a constant c, which depends on everything in the problem. So there exists a constant c, so that this measure of the set so this is asymptotic to constant x log x to the degree of L over f minus 2. So if this number here, OK, so maybe I should say OK, well, you can see that what are the orbits here? They're just all the s of a given size, because this acts 1 transitively and 2 transitively, blah, 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 up to n transitively. So that's interesting because you get logs for, I think, non-trivial reasons that are not just counting under hyperbolas. Another interesting thing about this is the power of log is sensitive to the Galois group. So let's say we have n is equal to 4. So this is 4. This is asymptotic to, OK, just with this, that's asymptotic to some constant x log x squared if g is Sn. But for example, if I let g be isomorphic to g be cyclic, then I get some other constant. I'll write c prime x log x cubed, because the sets of cardinality 2 break up into 2 separate orbits if this is acting by permutations. So OK, and then you could compute by hand all the other possible Galois groups for quartic fields. But I think it's really interesting that exponents are really telling us something about the extension. OK, so I should give you also an example where lambda is not 1. So these definitions mean something. So that's what I'll do next. I'll call that example 3.
What you end up counting and how you count.
OK, maybe I can skip to saying something quick about the proof. Yeah. OK. OK, fine. OK, so here's like a 5-minute proof sketch. Proof outline, I don't know. I'm not going to be able to say very much. So the natural object to study is the generating series. So I'm going to integrate over the set of automorphic characters, and I'm going to integrate the conductor to the S with respect to this Haar measure. And so the theorem boils down to showing that this has analytic continuation. So this converges absolutely for the real part of S greater than A, and continues to real part of S bigger than A minus. So you actually get 2m squared to the minus 1 with pole, simple pole, not a simple pole, a pole at S equals A. OK, so the first thing is to go from this global thing to some local thing. I'm going to so if LW over FV is a local extension splitting the torus, I'm going to let NT OW, this is going to be the image of the norm map from the integer points over the splitting field to the integer points downstairs. OK, and so So this series here is going to end up being a sum over. So these are not quite the global units, but the global units modified for this compact open instead of these standard ones here. And so it's going to be a sum over all of those, and then it's going to be a product over infinite places of over T, F, V dual. So here's chi of x, and here's the local analytic conductor at an Archimedean place to the s. And here's product over finite places of the same thing, chi of x over c over the conductor to the s. So this is going to be over this image of the norm map. Check. So here I have Lebesgue measure, and here I have counting measure. And here I've got, so this global unit makes sense across all places, and I have to look at these characters. So there's an application of Poisson summation that goes into proving this formula.
It's a lattice count, a Delic lattice count somewhere, because
Yeah.
the characters.
Yeah. So there's some of these finite places which are ramified, which cause me a big headache and take a lot of space writing the proof. But the pole is going to come from all but finitely many places that are unramified.
Not necessarily a simple pole.
No, it's not a simple pole. I mean, it's a pole.
You get the power of log.
It's a pole of that order. Yeah, that's exactly where the That's exactly where the power of log comes from. So let's say V is unramified. So in this case, there's several convenient facts, which I don't necessarily have in the ramified case.
And Poisson sum applied to what?
Poisson, where the lattice is the units.
Yeah, okay.
Yeah. So
As opposed to the Ripley or Kepler's, I mean, some have the duality Kepler's eventually coming out. That's what I'm aiming at. You see this, it's just
yeah, see what's.
Poisson sum on the units.
So there's a few convenient features here. So for one, okay, so let's say L over F is local now, local non-Archimedean, unramified. So this is map. The norm map is surjective in this case. Life is as good as you could hope. So then if I take the local Langlands correspondence and restrict it to the image of the norm map, you get that T, O, F, the characters of the integers, because here I'm counting characters of the integers now, the integral points. So this corresponds to counting this quotient of the H1 of the Langlands parameters. So it's LL cross into T hat. So if I want to count the chi here, I'm going to count the row here, and then understand what the analytic conductors are and count on this side. So you can also prove, again, using unramified, that this analytic conductor of chi, if it corresponds to a row, that this just breaks up as a sum. So the mu I are the co-weights, and I compose it with a row, and then it's the sum I equals 1 to the dim r. So at the unramified places so this is unramified for the torus, of course. At the unramified places, it does break up into one-dimensional characters. But this is not going to be true at ramified places. But I can kind of wiggle around it because I only have finitely many places I'm dealing with. And then here, this C is just the classical. I mean, here I've just got a character of OL cross. And I'm just kind of using some group theory to bound those characters. So my time is up. There's actually, maybe I'll just say in words, there's a really interesting thing that happens at the Archimedean places, actually. They turn out to be pretty fascinating. So there's actually a really deep result of pure analysis that I have to use to bound the integrals at the Archimedean places. It's something called a Braskamp-Lieb inequality. Yeah, yeah. At the level of generality.
Maybe you have to use it. What you're saying is you used it.
Yeah,
You
yeah.
don't
Yeah.
really have to use it.
Well, I used it, but so I mean, to really deal with a general representation of the L group, I can have, so this gives you a matrix of integers of like dimension of R by dimension of T. And in the general, I mean, so if you really want to deal with any possible representation of the L group, you have to deal with any possible vectors that come in that inner product in the Braskamp-Lieb inequality. So the only non-generality of it that I'm using is that the functions, the non-negative measurable functions, are restricted to be 1 over the function coming from the analytic conductor. Okay?
Is this to apply Poisson sum?
No. This is to prove the zone of analytic of convergence of these Archimedean integrals here.
So you've applied Poisson sum.
Yep.
And then you're facing, this probably has to do with identicals, right?
Yeah. But then this version due to Bout from 98 of this Braskamp-Lieb inequality that I'm using says that the inequality applies with a string of exponents if that point defined by the string of exponents lies in the convex hull of some convex polytope. And then to finish the problem, there's a combinatorial optimization problem that I have to solve to say for which S that integral is going to converge through the Braskamp-Lieb inequality. So I think the only non-generality that I'm using is that I'm not doing any function, but I'm just doing 1 over like this thing in the analytic conductor. So I don't know. So and I should also mention that there's a professor at ETH, Rico Zanklusen, he does combinatorial optimization. He's an applied mathematician, and he pointed out to me that optimization problem has to do with matroids and pointed me towards matroids and kind of gave me some ideas to solve that last bit combinatorial optimization problem for the Archimedean integral. So I'm already 4 minutes over time, so I should stop.